Hello, this is Mr. Smith with reading quiz number 2 on the trapezoidal rule. We've done other integration approximation techniques before, including the Riemann sums that was in the AB portion of the class. Now we take a look at trapezoidal rule, which, as you might expect, uses trapezoids to help approximate our values for integrals. So this all falls under the umbrella of what's called numerical integration. On the diagram below, you can see that I've used an example trapezoid from 2 to 3 to find the area underneath y is equal to x squared. Again, in AB calculus, we talked about using rectangles to approximate the areas under the curves. And if you remember, the rectangles that we used were sometimes rather inaccurate because of the shape of the function. In this lesson, we use a more efficient shape, which is the trapezoid. And what the trapezoid allows us to do is it allows us to have two heights that we're essentially averaging, the left and the right heights, in order to find the area of the trapezoid. Well, why does the trapezoid fit the function very well? Because it's the average of the left and the right rectangle approximations. Please note that it is not the midpoint approximation as we studied earlier in AB calculus and will return to later. So just a quick little reminder, the formula for the area of a trapezoid is the area is equal to the base, which in the diagram is 1, times the average of the heights, which in this case the average of the heights would be the average of 4 and 9. This is a little bit different probably than a formula that you memorized before because we were dealing with two bases and one height. The h and the b were switched. In our case, we're almost exclusively dealing with heights of trapezoids and two separate heights. So we kind of rearrange our formula for that. Okay, here's an example. Approximate the integral from 0 to 6 of f of x dx using n is equal to 6 trapezoids and the following data. So it's important to recognize that if we're using 6 trapezoids, one trapezoid will go from 0 to 1, one from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6, which makes 6 total trapezoids. So the integral from 0 to 6 of f of x dx can be approximated by averaging f of 0 and f of 1, multiplied by 1, which is the width or base of the trapezoid, averaging f1 and f2, f2 and f3, and so forth until we get to f5 and f6. Remember that if you're trying to cite a table or showing your work on a free response, you need to make sure that you use the function notation to indicate that you've used the table. Now when you go through and you plug in your values, the first trapezoid will have an area of 12 plus 10 over 2 times 1. So average the heights, multiply by the base. The second trapezoid will average 10 and 9 and multiply by 1, and so forth. So you notice that we're using every single value of the table. Some values you'll notice that we're using twice, and those particularly in this case are the middle values. We'll get to that idea in just a minute. When you add up all these values, you end up with the area of 74. It's also important to recognize that in the first two lines we're using the approximation symbol. Why the approximation symbol? Well, because we're not finding the exact value of the integral. We're using these particular data points to approximate the value. In example 2, the velocity in miles per hour of a Piper Club aircraft traveling due west is recorded frequently during the first 10 minutes after takeoff. Use trapezoids to estimate the distance traveled, area under a positive velocity curve after 10 minutes. So you'll notice that in this particular problem, the time intervals are not spaced evenly. So it's very important that when we try to find the distance, we take a look at each individual trapezoid rather than trying to find any particular tricks. In this case, we need to average v of 1 and v of 0, multiplied by 1, which is the width of the first trapezoid. In the second trapezoid, we average v3 and v1, but notice that the base now is 2 instead of 1. It's very important in an AP emphasis to make sure that you're finding the right lengths of each of your trapezoids. Be very careful and read your table closely. And we go through and find each of the areas of the individual trapezoids. Find the values, as you can see here, then add them up, and you end up with 765 miles in this case. And a quick correction, notice that the velocity is measured in miles per hour, and we want to find the distance traveled after 10 minutes. Well, that in fact would be 12.75 miles. We have to divide by 60 minutes per hour. Example 3. Use n is equal to 4 trapezoids of equal base length to estimate the integral from 0 to 2 of x squared dx. Well, you notice in this case that they don't actually give us a table, and we're going to use 4 trapezoids, so it might help us to figure out a table for ourselves. We need to divide the interval into 4 equal bases, each of which has a width of 0.5. The heights of each of the trapezoids will be the heights at 0, 0.5, 1, 1.5, and 2. We're just adding our width of 0.5 to each of our previous heights. To find the area of the trapezoid, we not only need width, but we also need height. The height at 0 is 0. That's what we get when we plug 0 into our function x squared. The height at 0.5 is 0.5 squared, or 0.25. And so on. You can see that we create all these heights. Height at x1, x is equal to 1, x is equal to 1.5, and x is equal to 2. Just as before, when we add these up, we need to average our heights. In the first trapezoid, we're averaging the heights at 0 and at 0.5. Remember, our width is 0.5 in this case, so be careful of that. Do the same for the trapezoid from 0.5 to 1, or from 1 to 1.5, and 1.5 to 2. When you average these up, you get your integral to be approximately 2.75. Now, the actual value of this integral is in fact 2.667. So this is a pretty decent approximation. So a question you might ask yourself is, can we simplify the rule at all? It seems like a lot of trapezoid areas that we're adding up. If you notice example 3, we've counted the inside heights twice. Those would be 0.25, 1, and 2.25. And the outer heights only once. That's because the left edge of one trapezoid is the right edge of the trapezoid before it. And so we end up counting the inside heights twice and the outer heights, which are on the edges of our interval, only once. So this leads to what is called the trapezoidal rule, a rule that can only be applied if we know that the widths of each of the trapezoids are equal. If you remember from a previous example, if the widths of the trapezoids are not equal, then we have to evaluate each of the trapezoids separately. And the way this formula works is, if our interval is from a to b, then we need to do b minus a over n times 1/2. And the 1/2 comes from the averaging of the heights. And then add each of our outside heights once and our inside heights twice. In this case, n represents the number of trapezoids, and h represents each of the heights. So let's apply this in example 4. Use n is equal to 5 trapezoids of equal width to estimate the integral from 1 to 2 of natural log of x dx. Again, we're not given a particular table, so we're going to write out all the possible heights and create a table for ourselves. So we need to divide the interval into 5 subintervals. The length of the interval in total is 1, so the length of each of our subintervals will be 0.2. We need to find our heights for every 0.2 units. So in this case, that'll be natural log of 1, the starting value, natural log 1.2, 1.4, all the way up until 2. And now we just apply the formula because we've got our heights and we know our width is 0.2. Notice that we're multiplying by 1 over 2 times 5 on the left. Well, that's 0.2 times 1/2, where that half comes from the averaging the heights. We get our answer to be approximately 0.3846. So thus, our approximation for the integral from 1 to 2 of natural log of x dx is 0.3846. Math number 9 estimates the value of the integral as 0.3863. Later on, we'll be able to find the exact value for the integral, but we are indeed pretty close. Finally, a last thing that's an AP emphasis, whether trapezoids over or under approximate. As we can see, and it's a little hard to see on this, but we'll look at it in class, the top of a trapezoid, meaning the line that connects the two heights, is in fact a secant line. And we remember secant lines from our very first unit when we talked about them and how they related to tangent lines. And secant lines approximate in the opposite way as tangent lines. You'll see in the picture on the left we have a concave up function, and the secant line goes above the concave up function, which dips below the line. So what does that mean? That means for a concave up function, the trapezoid approximation over-approximates. In the case of our right diagram, we have a concave down function. You can see that the secant line falls below the concave down function, which is curving upwards. In that case, our trapezoidal approximation will under-approximate. I find that drawing the pictures helps if you ever get confused about this. Also, making sure to connect it with tangent lines is also very helpful.